All right, today we're going to dive deep, and I mean really deep, inside the microchips that power pretty much everything in our lives. We're on the hunt for a hidden saboteur, a fundamental force of physics that is quietly, relentlessly working to destroy our electronics from the inside out. It's called electromigration.
You've definitely thought about this, right? Why does that smartphone or that laptop that was so blazing fast when you first got it eventually just slow down, get glitchy, and die? Well, it's not always just bad luck. More often than not, it's a slow, almost predictable process of physical decay happening at an atomic scale.
Okay, so what are we looking at here? This is basically a crime map for a microchip. Seriously, these red and orange hotspots are the areas where the chip is literally tearing itself apart. This map shows engineers where that silent battle against electromigration is being lost, and it's a dead giveaway for where a failure is most likely to start.
So, to understand what's actually happening in those red zones, we have to unmask this saboteur. We need to shrink ourselves down to the atomic level and see what this force of nature is really all about.
Okay, so here's the textbook definition for you. But what does that really mean? Just think about it. You have billions upon billions of electrons rushing through these unimaginably tiny metal wires inside a chip. Each electron is tiny, sure, but together they have a collective force, a real momentum. And this is the perfect way to picture it. That flow of electrons acts like a powerful, non-stop wind, or like a river current. It is constantly slamming into the metal atoms that make up the wire itself. Over months, over years, this electron wind physically pushes the metal atoms out of the way, slowly but surely eroding the very path it's traveling on. And this atomic shoving match leads to two catastrophic problems. First, when atoms get pushed away from an area, they leave behind an empty space, a void. You can think of it like a pothole that just keeps getting bigger and bigger until the road is gone. Boom, open circuit. The connection is broken. So where did those atoms go? Well, they pile up somewhere else, forming a hillock. And that pile can grow so big that it touches a neighboring wire, causing a short circuit. Either way, it's game over for the device.
Now you might think this all sounds totally random, like a roll of the dice. But it's not. Not at all. Engineers have gotten incredibly good at predicting exactly where and when this breakdown is going to happen. They basically have the saboteur's blueprint.
And this is it. This is Black's equation. It's like a mathematical crystal ball for chip reliability. It helps predict the mean time to failure, which is basically a fancy way of saying how long a circuit should last. Now don't worry about the math, just focus on two key variables here. J, which is current density, and T for temperature.
And here's the absolute crucial point. The relationship isn't linear, it's exponential. So a small increase in how much current you cram into a wire, or a little bump in heat, doesn't just shorten the chip's life by a little bit. No, it shortens it dramatically. These two are the biggest accelerators for electromigration by far.
And as if that wasn't bad enough, these two factors feed off each other. The current flowing through the wire also generates its own heat. It's a process called Joule heating. So you get more current, which creates more heat, which then makes electromigration happen even faster. It's this vicious, dangerous feedback loop that engineers are always trying to break.
So, armed with all this knowledge, how do engineers actually go on the hunt for these potential failures before a chip ever gets made? Well, let's get into the investigation. First off, they're looking in two main places. You've got your signal wires, which carry data. There, the current is bi-directional. It's sloshing back and forth all the time. But then you have the power grid wires, which deliver the juice. There, the current is uni-directional, a steady, one-way street from the power source to the components. And this difference is absolutely critical.
To figure out the risk, engineers use three different kinds of checks. Think of them as different tools. Average EM is for checking that slow, steady, long-term wear and tear. Peak EM is all about catching the damage from sudden, massive bursts of current. And then there's RMS EM. RMS stands for root mean square, and it is specifically designed to measure the heating effect from that choppy back-and-forth current we were just talking about in the signal wires.
So this begs a really good question, right? If RMS is so great at capturing heat stress, why isn't it used everywhere? I mean, shouldn't we use it on the supercritical power grid?
And the answer is actually really elegant and simple. Remember how the current in the power grid is a steady one-way flow? Well, because of that, the long-term average check already gives you the whole picture of the stress and wear. The RMS check is built for fluctuating currents, so running it on the power grid would just be redundant. It wouldn't tell you anything new or useful.
Okay, so we know what this thing is, we know how to predict it, and we know how to find it. So the final piece of the puzzle is, how do you actually stop it? Let's look at the countermeasures.
So first, you have to know the usual suspects. What causes these problems in the first place? Well, you might have some components that are just too power hungry. Or maybe the metal wires are just too skinny for the amount of traffic they need to handle, creating a bottleneck. Sometimes it's like a highway with not enough lanes. There just aren't enough parallel paths for the current. And of course, clustering too much activity in one spot creates hotspots, and we already know what heat does.
And thankfully, the fixes directly target these causes. If a wire's too narrow, you just widen it. It's like going from a garden hose to a fire hose. If one path is getting overloaded, you add more routes in parallel to share the load. And you can literally redesign the chip layout to spread out the busy components to avoid those dangerous hotspots from ever forming in the first place.
And this quote right here is why all that work is so unbelievably important. A chip can pass every single functional test you throw at it. It can look perfect. But if electromigration hasn't been properly dealt with, it's just a ticking time bomb waiting to fail months or years down the line. Reliability is every bit as important as performance.
So, that leaves us with one last big, provocative thought. We all want our technology to get smaller, faster, more powerful. But every step in that direction means cramming more current into even tinier wires, which is the exact recipe for making electromigration worse. So the question is, as we keep pushing the boundaries of physics, are we getting close to a limit, a point where this invisible enemy simply can't be defeated by clever engineering anymore? It's definitely something to think about. Thanks for tuning in.